So, hey everyone, my name is Manoj Agarwal. I'm an architect at Walmart. I'm joined today with my colleague Praveen. We are here to share how we do personalization on our e-commerce platform. So, Praveen, we can share the slides. Praveen, would you like to introduce yourself?
Yeah, hi everyone. This is Praveen. I work as a principal software engineer at Walmart Global Tech within the personalization and recommendations area. And I'm very excited to present our work at Apply conference. Yeah.
Awesome. Let's go to the next slide. So our agenda is actually pretty simple today. We are just going to walk you through the high-level architecture of our personalization platform. We'll walk you through the use cases that we have on Walmart.com. And then Praveen is going to take you deeper dive into a couple of areas around customer preference engine and our feature and model store. So Praveen, next slide, please. So we have hundreds of millions of customers across the US and international markets who are shopping at Walmart across our thousands of stores and our websites. So this diagram shows how, as we look at the data about our customers through different channels, the picture of customer becomes more and more complete. So looking at the data of only one channel enables you to focus on customer behavior of only that channel. But to understand our customers more holistically, we need to be able to look at the broader picture and the holistic picture of what our customers are doing. So with that, let's start by understanding more about what personalization and recommendation does for our business and for our customers. So next slide, please. So some of these use cases may just be an example for the e-commerce experience, but they also equally apply to the other channels as well, like in-store purchases and things like that. So basically the customer journey, it spans different stages of acquisition, stages of finding products, deciding the most relevant product that a customer may want to purchase on either our e-commerce platform or in-store, and finally converting or making the purchase for those items that they're looking for. So customer journey, it also includes the experiences after the purchase, like changing or amending their orders, handling substitutions, recommendations in case of out-of-stock items. So again, for personalization and recommendations, as a customer is going through these different stages, majority of these experiences are what we call zero query problems. So what it means is that, for example, when customer opens our application and lands on the home page, the customer has not fed us any query into the app to tell us what she's there to do, right? So we have to rely on what we know about the customer prior to the start of this session. So we have to rely on what her preferences could be, predict what her intent could be to come to the Walmart app, and then paint our homepage based on those intents. As customer engages and interacts more during these stages, with different experiences that are presented to her, we are able to also build a better view and better predictions of what her intentions could be in the given session. So it helps us shape customer's experience and tapers it towards her exact needs in the current session and allow her to convert with a seamless and consistent experience. So as we look at these different stages in the journey, there are several dozens of recommender systems that are in play in the background. They enable us to find the most relevant content that we can show to the customers. So again, taking the homepage as an example, if the customer is a repeat grocery customer, then we want to make sure that the recommender systems at play, they help the customer build their basket very quickly, because grocery baskets can be very big, almost 25 to 30 items typically. And adding each item to the cart can be time consuming for the customers. So we provide a personalization module right on the homepage that allows customers to add 10 to 15 items to the cart with a single click. That significantly reduces our basket building time and allows customers to complete their journey with efficiency. Apart from that, we also have recommendations that allow customers to discover new products. It's not only just about purchasing what she has purchased in the past, but also looking at the other sections of the inventory that you might not have engaged in the past, which probably you have shown interest but not converted in the past. So these recommendations, they also contain seasonal and event-based content as well. Like we have, like, let's say Father's Day coming up next month, or rollback event coming up. So understanding what relevant content could be shown to our customers at different stages of their journey. So currently, personalization serves billions of product impressions across the entire ecosystem of our customer journey. And aside from just product impressions, we also personalize non-product related content like banners and badges, what to show to in what context to the customer. All of these different contents, they are in a way the language which we speak to our customers, by telling them that we know them, we understand their needs and their intent, and that we are there to help them build their basket with the right items that they're looking for. For these predictions to be right, we need to understand the customer intent at the micro level. And we'll talk about that micro intent in detail in upcoming slides as well. So basically, the idea is that customer's intent, it can shift multiple times during a session. For example, they might start by shopping for produce items, but immediately switch over to shopping for pantry items, and then maybe to bathroom supplies and baby care products. So our inference engine has to be able to understand the shift of the customer's intent and adequately move based on that. So the customer doesn't see a lot of friction points in our journey. In the cart, there are two kinds of recommendation experiences that we provide. One is that we call post add to cart, or PAC in short. Another one is called last call experience. So post add to cart, as the name suggests, it shows recommendations based on the items that you have in your cart. So it shows, for example, items that may go well with the items that you have added into the cart. Whereas the last call experience, as the name suggests again, that is the last reminder for you before you hit the checkout, to see if there could be other items that you might be interested in. So this the last call is actually kind of mimicking the behavior of the checkout aisle in the stores. So it might have like low consideration items like candies or batteries or other things that our prediction engines recommends that the customer would likely buy at the time of the checkout. So and for these cart experiences, like last call or post add to cart, for all of these, the objectives of the recommendation system is different. In the last call, typically we don't want customer to go back to the discovery experience again. We want they have made up their mind to check out, and we want to make sure that they still go ahead and proceed to check out. So, so these are the different areas in which we provide recommendations. Praveen, next slide, please. So this picture actually it represents high-level architecture of, we can say, probably any ML system. So we have a data lake. With that data lake, we have multiple different kinds of data processing units attached. So there are batch processing, stream processing, on-demand processing kind of data processing units. They do typically feature engineering and basically data transformation. Eventually, all the data is used for model training and testing. Once the model is ready, then we store that in model store. All the features go to a feature store. And from model store, basically model store supports multiple versions of the models. And there it's picked up, the model is picked up by the inferencing service. And that's how it gets plugged into the application. And then the feedback loop completes by application providing more and more data, maybe like click-through rate and other feedback to the data lake that is used again for further training. So there is nothing new. I'm sure that anybody attending this conference, they have seen this kind of flow multiple times. So I won't spend much time on it. Praveen, next slide, please. So yeah, let's talk a little bit about the intent, since I have been mentioning that for a while. Here we are introducing the concept of what we call as micro intent, mainly because intent is dynamic in nature and it's applicable in a given context at a given time for the given customer. So in this example, what we see is, let's say the customer is trying to arrange for a party. So first she starts looking at the party supplies that she needs. She's adding plastic forks, spoons, and other utensils, and then immediately she starts looking for ice cream, because her micro intent has changed from trying to get party supplies to getting the food or the grocery for the party. And then she moves on to adding gift cards. Maybe she's looking for return gifts or something like that. So this is just one example of how the intent or the micro intent comes into play in the given session. So in addition to data, we also pay a lot of attention to detecting the micro intent of the customer. So our inferencing engine can actually shift accordingly. So let's move to the next slide. Praveen will walk you through the details of the recommendation engine and personalization system.
Thank you, Manoj. It was a very good overview of the personalization area and the recommendation area. And also, you have discussed very good about the intent area. So coming to the what exactly the customer preferences, how do we actually come up with a model? So we'll just give a high-level overview of some of the feature data what we use within the customer preferences model. So here you can actually see like an example where we are trying to capture all the historical information about a particular customer, what are the different item views, what transactions the customer has made, what are the different items he has actually added to the cart. And as you can see, we actually try to learn about using these historical features, different model weights, and we are actually trying to predict at a future, time interval, what items the customer has a high probability of purchase. So for training the model weights, we actually use a variable time window here, like different periods of time, like a 5-day period or a 10-day period. And then and you can actually see an example that we use a historical information until from March to January 2021 to predict future what a customer can actually has a high probability of prediction in February of 2021. So coming to a real world example of how a customer context actually works in the re-ranking of any kind of an item recommendation pool, underlying item recommendation pool. So you can see an example here. What we are presenting is there is a customer who actually we have identified he or his customer context to being like he or she might like iPhone product. And by learning that customer context, there are a couple of things we can also predict, as part of this journey, right? So one is, given the product iPhone is actually, we can also predict what kind of a price bands the customer actually can also might buy. So with that, both the price band and the brand affinity data, what we call it, for customer understanding, we can use this set of customer context information to re-rank the item, any kind of an underlying item recall set, to actually highlight the items which has a very high probability of purchase at any point of time. So here you can actually see what we call it as a customer understanding ranking algorithm, which actually is a function of the underlying item recommendation pool relevance score, and it also considers the item attribute understanding, like what we discussed. For any given product, what is the brand, what is the price band for that particular item, and also takes into the consideration the customer context. Here, for example, there is a different scoring, brand level affinity scores available for any given customer, and also the price level affinity scores are also available for any given customer. So with both this information all together, we are able to actually see the example here to re-rank the items from the AirPods item actually has been re-ranked to top of the item recommendation list, and the remaining items were actually re-ranked below. So this is a very good real world example how we actually use customer understanding preferences data. So coming to at a very high level, how do we actually build the customer preferences engine? As you can see here, you can see on the left-hand side the item recommendation flow, and we actually have a little more detailed oriented of how the recall set scoring architecture actually looks like. So if you look at the left-hand side picture, which is like we actually have able to gather the recall related information by using the user to item interaction data. For example, like what are the items which are viewed and also added to the cart. Using this information, we form a recall set, and then we also actually extract, the item interaction, user to item interaction embedding data out of it. And from the item catalog data, we are also able to generate the item embedding vectors, which actually can be used, to find the similarity of different items. And also there is a pairwise item attributes being extracted from the item catalog. And all these different feature data has actually been fed into our, the pairwise scoring algorithm. What we use, it is a wide and a deep, algorithm. We actually combine both the wide and the deep to minimize the loss function at the very last layer, and to actually provide us a pairwise score. And we using this relevance scoring data, we are able to present a good recall set which customer has a high probability of purchase at any point of time. So moving to the next slide, we are also talk about one of the use cases. How do we? I think one of the use case is also how do we actually generate the recall set at a faster pace, in the sense like by keeping the latencies very low. So here for the use cases, what we use to actually gather all our embedding data, we kind of use the Milverse AMN platform, where we have different collections of the embeddings data. As you can actually see, is represented one embedding set being like targeted towards to find similar item embeddings, whereas another embeddings are targeted towards customer embeddings, and there are different kinds of collections of the embeddings actually being created into the Milverse platform. And using this data, we are able to fetch on a real-time basis at any given point, given any anchor item. Let's say if I want to find a similar items, we can actually able to query the Milverse platform and find what are all the different similar items for a given item embedding within its embedding space available. And this is one of the very good example of how do we actually efficiently generate the recall set information, so that your model coverage can be very high, rather than preloading all the inference batch infer data into like a backend data store and only serving the data if the data is available in the data store. Rather than that, if you actually move some of the use cases towards this Milvus platform, you can actually efficiently improve the coverage of your model since you will be accessing this data on a real-time basis. Coming to a combined or a in detailed architecture of how our feature and the model store looks like. As everyone know, like for building a good real-time inference platform, you need to have a very good feature store available, and also that feature store should be also accessible for real-time inference at a low latency. Because the real-time calls are very latency, you have to keep the latencies very minimum, right? That's your main goal. Otherwise there is a chance that the customer we might lose the customer if the time it takes the recommendations to load is very long. The customer might move away from that recommendation module altogether. So it's very important to keep the latencies very low. So as Manoj actually mentioned, the session-related context plays a very important role in the context of customer and intent understanding. So we focus very much on stitching the events on a real-time basis, or aggregating the data of a session context, so that we actually use this data for a real-time inference, so that we can actually provide a better recommendations to the customer, because the customer intent might be changing within a particular session itself based on what items or transactions he's making. And you can see here, we are also aggregating, in terms of the feature store, we also aggregate the data from different feature store, and also we keep the the data latency to very low, and also it helps us to build a very very useful and a stateful session related context for a given customer to predict what is the intent and what is the understanding of that particular customer at any given point. And we, on the other side, you can also see that there is a model store where we actually use to store all our trained models, so that we can also able to easily A/B test all the different models to identify whether the new version of the model is performing very well compared to the old versions, and if not, like what are the steps we need to take by using the feedback data to retrain those models. Coming to the next slide, which is a detailed architecture view of our online inference and serving platform, which actually plays a very critical role in predicting a intent of the customer at any given session, what a customer is doing. So here we have like we have completely built this online inference platform in a Kubernetes cloud environment, and we are also kind of being like a multi-cloud. As a Walmart has different operates with different cloud partners also. So we want to use the whatever the platform we have built can be easily be deployed across different cloud partners, right? So as you can see here, the as part of the online inference platform, so a couple of things what we did to ensure was like this platform is a multi-model supported platform. So what that means is like a data scientist member can actually bring either a TensorFlow model or a PyTorch model or like Onyx, any kind of a model they can actually bring to this platform, and they can easily able to like spin up a microservice out of this model. And we are also providing a couple of interesting features where you can also tie different kind of models together. as an ensemble fashion. So in the sense like if you need to interact, if you have like a two independently very focused models and you want to actually kind of build them as an ensemble model also, so that you want to take you want to fed the output of one model into as a features into the second model. You can also be able to easily do that by using a configuration where you can actually tie both these models together, right? This as you can see that we have built a something called an inference graph, which is at a very high level. So the concept of this, the main idea of the inference graph was there are two things. One is like we want to expose a human readable APIs to all our clients, because majority of the time the models usually take embedding vectors or the features which were probably not only the engineers or ML engineers or the data scientists or whoever working on the model can easily understand. But to actually build a platform, you need to have a proper human readable APIs. So this inference graph, what it does was we expose the gRPC or REST APIs out of it, and this inference graph also has the capabilities. Given a feature, it actually can automatically talk to like a feature store to gather all the features which are required, and also call based on the configurations which you how do you configure your model configuration. It has a set of pre-processing steps and the post-processing steps also, which you can actually configure, so that to give an example of a post-processing, let's say we have some business use cases like for a particular model, we only want to show like items which can be delivered to your home rather than the items which you can actually pick up in the store at any given point, right? So to actually handle these different kinds of cases, we actually use this post-processing as kind of a filtering mechanism of the the recall set which is generated from the model, and basically takes the output of this post-processing model and responds back to the clients. And a couple of other things you can also notice here was we envisioned this inference, real-time inference platform handles both async and real-time calls. What that means was there are some cases where you actually are doing some kind of a predictions and updating those prediction scores into some kind of a data store where you actually do the predictions in such a way using a Lambda architecture or something like that, where you do the capture or regenerate these predictions by customer interaction events or something like that. So we actually use streaming jobs in those cases to to find the prediction score and then update into the data stores also. Yeah, so this is at a preview of what our talk today about intelligent customer preferences platform is. So yeah.
Awesome, guys. That is super cool. I want to ask a few questions from the chat because we have a minute before the scheduled time. In the meanwhile, while we are waiting for the questions to come in, I think there was a really cool one that I'd like to see what you all think about it. It's asking about feature stores in general. Does a feature store contain pre-computed features for all possible online inputs in order to avoid the need to compute features in real time during inference? Or is it used differently to speed up inference?
Yeah, so for online use cases, it's used exactly for that purpose, that you already have the feature computed, available there, and we use that to enrich the inferencing requests, right? But feature store has many other purposes, right? We use that to save compute costs for model training. So if we have already spent some compute to calculate the feature, compute the feature, then we store that intermediate result or the final result in the feature store. and it can be reused when we are training some other model if they need that same feature, or retraining the same model next time. So, but yeah, for inferencing, it's absolutely that same use case that we just refer to feature store to enrich the request, and at runtime we don't have to do all that feature engineering.
Excellent. Sweet. Well, thanks, guys. It looks like the chat's pretty quiet. Anyone that wants to throw any questions in here for Manoj or Praveen, feel free to hit them up on Slack as usual, as we've been doing all day. Manoj, it's great seeing you again, man. And I hope
Yeah,
that
same
you
here.
can come back on the MLOps community podcast sometime soon and talk all about this.
Yeah, looking forward to that.